Yeah.
Okay. So let me just welcome you all back. So I hope you had a wonderful summer. Join us for the colloquium. We're going to have what I did on my summer vacation event at 11. We're starting early. Thank you for accommodating the earlier start so that staff has time to reset up and get the computers going so that things can begin at 11. But Helen, have you introduced yourself? Maybe you could say a word, and then and Jacob.
Yeah, sure. Hi, I'm Helen. I'm a postdoc here now. I just started, and I'll be helping facilitate the foundation seminar along with Prashant, who will be my co-lead. So our first speaker, thank you so much for agreeing to give the first talk, is Jacob Barandes, and he will be talking about the Stochastic-Quantum Theorem and quantum gravity. Okay.
Thank you very much. I'd like to thank Prashant and Helen. Thank you so much for the lovely invitation for hosting me. It's really wonderful to see all of you. I'm really excited to be here. All right, let me get started. We have an ambitious agenda ahead. So this talk is based on two papers. Those are the archive links and the PhilSci links, whichever you prefer. Good. All right. I'm going to start by talking a little bit about this issue of incommensurability of theories. So the theory of general relativity, you'll note, it's based on physical matter evolving in 4D spacetime and contains a large class of diffeomorphism invariant physical quantities. Textbook quantum theory, on the other hand, this is the theory based on the Dirac von Neumann axioms from the early 30s, is an instrumentalist and operationalist recipe that predicts only measurement outcomes, measurement outcome probabilities, and expectation values that are defined as statistical averages of measurement outcomes weighted by measurement outcome probabilities. A lot of background noise coming in. So from a basic conceptual standpoint, these two theories are phrased in manifestly incommensurable ways. Now, in the approximation of a fixed background spacetime and assuming a low energy long wavelength limit, you can actually make these two theories work together. In this limit, quantum field theory takes precedence. One can then write down an effective quantum field theory for general relativity and calculate scattering amplitudes and perturbation theory. There's a variety of other things you can calculate too. You can calculate the first quantum corrections to Newton's law in the solar system, and you find ridiculous answers like it's a 10 to the minus 70 correction. You can actually do these things. But textbook quantum theory does not legitimize assuming any sort of physical reality underlying such calculations. Again, because this is the regime in which quantum theory takes precedence, and in quantum theory, at least textbook quantum theory, you're not making any statements about what's physically going on, only measurement outcomes and measurement outcome probabilities. Famously, we also lack a more complete theory, UV complete theory, a theory that's valid at all scales that would combine quantum theory with dynamical general spacetimes. By construction, any such theory should ostensibly provide a framework in which gravity and quantum theory are no longer phrased in incommensurable ways. Either they're both phrased in a way that they work together, or they're replaced with something else. But there should be, if there's really a unified theory that combines them, this issue of incommensurability between the two theories should dissolve in some sense. So here's perhaps the most obvious expression of this incommensurability. So here's the original Einstein field equation, right? This is the basic dynamical law of general relativity. Here it is. We've got the Ricci tensor, Ricci scalar on the left. That expresses the curvature of spacetime. And on the right, we have the energy momentum tensor T mu nu, which expresses the distribution of matter, mass, energy, momentum, pressure, all that on the right-hand side. So as a first guess, one might try to replace the energy momentum tensor T mu nu with a quantum operator T hat. Right, you get this expression here, and then of course this doesn't really make a lot of sense because the right-hand side is an operator. It doesn't have a specific definite numerical value. So we have this thing called semi-classical gravity, where we attempt to replace T hat with its quantum expectation value for some quantum state psi, and we get an expression that looks like this. And this is something you'll find in books, Wikipedia, articles. So there are various mathematical conceptual problems that arise from this replacement. For example, if you consider superpositions where you have a lot of mass over there and a lot of mass over there, then the average is like in between, but that's not really how things work. But there's a deeper problem. The most basic problem is that this just doesn't make any sense. It just basically makes no sense. Why doesn't it make any sense? Because textbook quantum theory is crystal clear that quantum expectation values, like that thing on the right-hand side, is an average of measurement outcomes over measurement outcome probabilities. That's it. It's not an average of phenomena physically happening, even though we often pretend that it is. We often pretend that it is because this distinction, when you're doing tabletop experiments, you can kind of elide it, even though axiomatically textbook quantum theory doesn't legitimize that. But here, you're putting on the right-hand side an expression that has to do with measurement outcomes, not physical stuff in space-time. So this just doesn't make any sense. Well, we have some options. We could instrumentalize, operationalize general relativity, turn it into an instrumentalist, operationalist theory. So maybe that's what we have to do to eliminate this incommensurability. In a sense, that's what's happening in specific examples where quantum mechanics and GR play somewhat well together, like in bulk boundary dualities, like in ADS-CFT. Here we have quantum gravity in a bulk spacetime, and we're defining quantum gravity in some purportedly emergent sense in terms of a quantum field theory defined on the boundary. So in this case, we're taking quantum field theory again to be the basic theory. It's an instrumentalist, operationalist theory, and general relativity is supposed to just emerge in some sense from this. So far, however, these examples appear to depend on special features of the boundary that make it tractable to place or define a QFT there, and implicitly also put measuring devices there. Because after all, for an instrumentalist, operationalist theory like textbook quantum theory, all of the predictions are by definition measurement outcomes and measurement outcome probabilities.
Do you have to read it as quantum field theory is in ADS-CFT? Do you have to read it as quantum field theory is fundamental and gravity is secondary, or could you read it the other way around?
That's an interesting question. So in ADS-CFT, the CFT is rigorously defined. It's a UV complete theory. The bulk gravity theory is not. So it's certainly the case that sometimes the CFT will be strongly coupled, or it will be difficult to do calculations with it. And then you can, in those limits, often the gravity side will become more easy to calculate with. And so we can do calculations on the gravity side using, quasi-quantum-ish gravity. But often we can get by with reasonably classic looking calculations and then predict what the CFT is going to do.
Right.
But in terms of defining the theory in the UV complete sense, you need the CFT to do that. So other approaches rely on lower dimensional spacetimes. There's been a lot of really interesting work with the SYK model and JT gravity. This is 1 + 1 dimensional gravity, and there's all this stuff with wormholes and stuff, but now it's a lower dimensional spacetime. There's been a really interesting work with summing the partition function for 3D gravity and stuff like that, right? So these approaches all represent what I would argue is another stage of retreat from scientific realism to instrumentalism and operationalism. Instrumentalism, again, being the viewpoint that our physical theories are just tools for making predictions and we shouldn't read too much into them, and operationalism just meaning that the things that we define in our theories are defined by the operations we do to either measure them or calculate them. And that's it. We don't make any claims about what's going on physically. And that's an option. Maybe that's the way we go. I'm not saying that that's wrong, but well, maybe there's another option. Maybe we should instead reify the ingredients of quantum theory. Maybe take quantum theory and make that a more physical and less instrumentalist or operationalist theory. What ingredients are available to do this? At least in textbook quantum theory. Well, we've got Hilbert spaces over the complex numbers. We've got state vectors or wave functions. We have density matrices. We have self-adjoint linear operators representing our observables. We've got time evolution operators. We've got Hamiltonians. We have a lot of ingredients. Maybe we should try imbuing some of these with some sense of physical reality, and maybe that will help bridge this incommensurability gap. Well, one obvious problem is that these ingredients don't live in 3D space or 4D spacetime. So wherever they live, they don't live in the kind of place that's commensurable with the kind of things that live in general relativity. That's an immediate problem. So it's not quite clear that this is going to resolve the incommensurability problem. But maybe what we have to do is take where these things live as the seat of reality. Maybe reality really is happening in some Hilbert space and the state vector is some physical thing. And what we think of as space-time is emergent, but now it's not emergent from an instrumentalist or operationalist theory. Maybe it's emergent from a physical theory, just a physical theory that lives in some very unfamiliar kind of space. Well, there's a problem with this too. So a reason to be skeptical about assigning a physical meaning directly to these Hilbert space ingredients is that quantum theory contains a relatively unrecognized form of gauge invariance. So if you let V of t be any time-dependent unitary operator, the following gauge transformation leaves all empirical predictions of quantum theory invariant. You take all your state vectors of wave functions and multiply by this time-dependent unitary. If this were a time-independent unitary, this would just be a basis transformation. But remember, V here is time-dependent. We're changing basis differently at each moment in time. Density matrices transform by a similarity transformation, as do observables. Time evolution operators transform a little bit differently. So note the t equals 0 there. They transform as what are called gauge correlators, right? Because you need to transform from objects that live at time 0 to objects that live at time t. And Hamiltonians transform exactly like a non-abelian gauge potential or a gauge connection. Interesting. This is exactly the same formula that one uses to transform the gauge fields of QCD or another Yang-Mills non-abelian gauge theory. This was first written down, at least as far as I was able to determine in its general form, by a philosopher of physics, Harvey Brown, in 1999, in the context of trying to understand Galilean transformations and transformations between inertial and non-inertial frames in non-relativistic quantum mechanics. But this is kind of disturbing, because when you see a bunch of objects that transform this way, at least if you come from maybe a high energy background or a condensed matter background, you become very skeptical that these are reliable ingredients, right? Any more than we would call the gauge potentials of electromagnetism reliable ingredients, because you can change them in these incredibly radical ways and it has no effect on the observables. And the fact that it's not merely like an unobservable change, but it has exactly the same form as non-abelian gauge transformation is a pretty scary signal. So all these Hilbert space ingredients are gauge dependent, makes their physical meaning highly suspect. Indeed, you can actually map any state vector trajectory in the Hilbert space to any other state vector trajectory, because you can do this unitary rotation differently at every moment in time. Therefore, a state vector trajectory doesn't actually contain any gauge invariant physical content. There's actually a very lovely analogy between this kind of gauge invariance and the whole problem, the problem of space-time substantivalism in GR, with Hilbert spaces and Hamiltonian playing somewhat analogous roles to manifolds and metric tensors. You can do a diffeomorphism transformation and replace your manifold and metric tensor with maybe a very different looking manifold and metric tensor with no physical consequences. This is kind of the analogous thing. What is gauge invariant in textbook quantum theory? Well, like I said, these transformations preserve all the predictions, and those predictions are measurement outcomes and measurement outcome probabilities and averages of the former over the latter, expectation values. But then we're right back to instrumentalism and operationalism again, the only ingredients that are gauge invariant. So this doesn't look terribly promising. All right, so let's take stock for a second. Let's ask some questions. What ingredients can we find to provide a genuinely physical foundation for quantum theory, if any? While we're at it, why is quantum theory based on the complex numbers, Hilbert spaces, linear unitary time evolution, and the Born rule anyway? Anyone know? Quick hands? Anybody?
What the books say.
What the books say. Okay, good. Excellent. What the books say. Good, that's a good answer. What connection, if any, is there, by the way, between, I don't know, I'm just going to pull this out of the hat, stochastic processes and quantum theory? I mean, they both involve probabilities, they both involve vectors, matrices. You might, wonder about a possible connection between these things. I don't know why. And if we're talking about stochastic processes anyway, how does one justify the Markov approximation, often used for stochastic processes? How do you justify that on theoretical first principles grounds? For those of you who do Monte Carlo simulations, you're probably familiar with, Markov chain Monte Carlo. That's the first place I learned about Markov chains. Actually, the second place I learned about them in a linear algebra class at college. But how do you justify the Markov approximation? It's actually not super obvious how to justify it in a rigorous way. We'll often assume that we have a stochastic process that has the Markov approximation, and then we'll see if it aptly describes reality. But in order to justify it, you'd need something more general, and then you'd need to somehow show theoretically that the Markov approximation emerges. It'd be nice to have such a theoretical first principles argument rather than just saying, well, we try it, it works. And why has there been so little work on developing a fully probabilistic generalization of general relativity at this point? Like a fully probabilistic generalization, not just adding like a noise term, but like, replacing the Einstein field equation with something that's genuinely at its root probabilistic. Wouldn't that be a pretty obvious stepping stone to quantum gravity? Is it interesting that we haven't done this first step, considered, trying to develop a not quantum probabilistic theory of gravity? That's interesting too. All right, let's lay out some empirical facts on the ground as we proceed here to maybe guide our work. Here's what we consistently and directly find in experiments. We see definite measurement outcomes. We see probabilistic behavior that converges over many trials. Closed systems evolve in a way that mathematically we know we describe with unitary maps. We don't see, at least locally, a preferred inertial reference frame, at least if we're not thinking cosmologically. We also, and this is crucial, whenever correlations show up, new correlations between systems, they always arise from local interactions. We don't see new correlations appear non-locally. That said, some experiments look spookily non-local, but yet we can't use them to send controllable messages or signals. What have we never actually directly observed thus far? Well, we've never actually seen a Hilbert space over the complex numbers. At least I haven't. If you haven't, please let me know. I'd love to hear your experience. Although if you watch that Oppenheimer movie, they show like all these beautiful sparks and fields of stuff. Maybe that's Hilbert spaces. We've never seen state vectors, wave functions, or density matrices. We've never seen pilot waves, or for that matter, multiple universes, branching or otherwise. Wouldn't it be nice to have a formulation that affirms all that, the whole list of empirical facts that we directly observe, while being general and model independent enough to accommodate particles, fields, discrete systems, what have you, while being compatible with the no-go theorems, minimizing any speculative metaphysical hypotheses or SMHs, and that's very intentional, without relying on reifying that list of things that we don't directly observe, Hilbert spaces, wave functions, and so forth, and ideally replacing the instrumentalism operationalism with a physical substrate. How do the existing approaches and I don't know, interpretations of quantum theory stack up? How about your favorite interpretation of quantum theory? You can take a moment. Okay. So in this talk, I'm going to present a new formulation of quantum theory that arguably satisfies all these objectives. Why wasn't this discovered before? What is our unfair advantage today? Well, this formulation depends on concepts that were not available in the 1920s when people explicitly abandoned trying to find a physical picture of reality. Heisenberg and Pauli, these people were very clear that they gave up on trying to find a clear physical picture, and they wanted to embrace an instrumentalist operationalist approach to quantum theory. This was the 1923, 24, 25. And some of these ideas weren't even widely known until the 2000s. So stochastic matrices, this is actually an old idea, but they weren't widely used until the 1950s, so decades after quantum theory was pretty much calcified as we currently understand it. If you look up stochastic matrix or stochastic matrices in Google Ngram, the Google Ngram here, you'll see that there's just this spike that happens in the 50s. Unistochastic matrices in particular, which I'll have a lot to say about, were introduced by Horn, a mathematician in 1954, in the context of his work on linear algebra and analysis. Originally called these orthostochastic, but then they were renamed and generalized to unistochastic by Thomson, another mathematician, in 1989. And then, very importantly, a concept called an indivisible process, which was introduced by Mikhail Wolf and Ignacio Chirac as recently as their 2006 preprint. 2008 is when the paper was actually published. So this is like hot off the press, practically. Indivisible processes are a distinct and, as we'll see, very important way to generalize Markov processes. Okay, so this new formulation will be based on the following theorem. Here it is. This is the stochastic-quantum theorem. Every generalized stochastic system can be regarded or realized as a subsystem of a unistochastic system. All right, so together with the fact that a unitarily evolving quantum system, as I will explain, can be regarded as a unistochastic system in disguise, this gives us a deep correspondence between a wide class of stochastic processes and quantum systems. Now, of course, we'll have to define the terms that show up in this theorem. What is a generalized stochastic system? What is a unistochastic system? And what do I even mean by a subsystem in this context? I'll be very careful about defining all of this. I'll also need to give you a dictionary that will translate between the two sides of this correspondence. On the one side, this class of stochastic systems, and on the other side, quantum systems. But then we're going to get a dictionary that lets you translate between the two. So you'll be able to take any question about quantum systems and run them through this dictionary and ask what is happening at the level of this much more physically transparent stochastic process, and vice versa. Okay, a little bit about the theory of stochastic processes, and this gives another motivation for this whole project. So when modeling a real-world macroscopic system that behaves probabilistically, one often uses the theory of stochastic processes. This comes from the Greek stokos or stochastikos for aim or guess. And again, as I said, one often resorts to various simplifying approximations to make these models tractable, like the Markov approximation, or, as I'll explain later, divisibility. I'll show that there exists a highly useful formalism for modeling a large class of stochastic processes without making these approximations. As far as I know, there is no such general formalism in existence today. Although maybe there is. The formalism will turn out to be quantum theory. Okay. So in a sense, just as you take classical mechanics like a Newtonian system, and you have analytical mechanics, right? You can rephrase it in terms of the Lagrangian formulation or the Hamiltonian formulation or the Hamilton-Jacobi formulation or whatever. And this is good for studying the system, proving theorems, studying questions like ergodicity, but also for, you have a systematic way to craft systems now, right? You can craft a Lagrangian, give it the properties you want, and then see what the system will be like. You can impose symmetries on an action. It's much easier to impose symmetries on an action and then derive what the equations of motion are going to be. So it gives you like a canvas for painting whatever kinds of systems you want. That's the magic of analytical mechanics. Well, the claim is that generalized stochastic systems, right, which is this broad category of stochastic processes, which include Markov processes and many of the stochastic processes that we're familiar with, they have their own analytical mechanics, but that analytical mechanics is just quantum theory. In its path integral formulation, which is like the analog of the Lagrangian formulation, the Hilbert space formulation, which is like the analog of the Hamiltonian formulation. And as a side note, this potentially opens up a new class of applications for quantum computers and quantum simulators, because if I can take any, very general kind of stochastic process and then read it across this dictionary and rephrase it as a quantum system with some Hamiltonian, in principle, I could run it on a quantum computer. All right, so another way to think about this is to look at the following grid, right? So we've got classical physics and quantum physics, and we have different formulations. There's the ontological formulation, the most transparent physical picture of what's going on. Then we have the functional formulation and the first order formulation, where we package together some additional ingredients with the system's configurations to give you nice first order differential equations to encompass the laws. So for classical physics, we have the following entries. The standard Newtonian picture or Maxwell equation picture, the picture where I just give you what the system is, what its degrees of freedom look like, and what are the equations that they satisfy. That's the first box. That's the most physically transparent one. But once we have that, if it's available, having a Lagrangian formulation, we can phrase things in terms of like varying an action functional, makes it better to study symmetries, still based on configuration space. We have the Lagrangian formulation. And then if we're willing to package some additional ingredients with the configuration of the system, for a system with second order differential equations, this generally means packaging momenta together with configurations, getting a phase space. Then we have a nice first order formulation where you can talk about the equations of motion as first order differential equations. Well, for quantum physics, we have a functional formulation. That's the path integral formulation. We have a first order formulation where you package ingredients together and you get first order differential equation, the Schrodinger equation. That's the Hilbert space formulation. And then we have this question, what goes in the box? Well, the claim is that we can now fill in the missing piece of the box. This missing piece, these are the generalized stochastic systems. And the claim is that they'll give quantum theory a physical ontology that in principle could make it more commensurable with general relativity.
Sorry, Jacob, by functional, you mean it in the mathematical sense, right? Or also in the philosophical functionalism?
No. I mean this in mathematical sense, not functionalism.
Okay.
Yes, I don't mean, this is like based on functionals.
Yes.
Yeah, good. Thank you that's the excellent point. All right, so what's this whole thing about non-Markovianity and divisibility that I keep emphasizing? Well, identifying and removing hidden assumptions is often a key step toward discovering new science. In particular, we'll see that avoiding the assumption of the Markov over divisibility approximation will be crucial for deriving quantum theory. These were key missing pieces historically. That's why earlier efforts going back to Bopp and Fenny's and famously Nelson's stochastic mechanics didn't end up panning out. They just all assumed that they were trying to recreate quantum mechanics using stochastic processes, but they assumed the Markov approximation from the beginning. I guess they just didn't think that it was worth considering more general kinds of stochastic processes, or maybe they just thought it was too intractable. There was no general formalism for more general kinds of stochastic processes. But there's been a lot of work in recent years suggesting that quantum theory is really fundamentally non-Markovian. There's a paper I particularly like by Glick and Adami that talks about this, but you also see people talking about non-Markovian effects in open quantum systems nowadays. Okay, so we need to review a couple of things, how standalone probabilities work, joint probabilities, conditional probabilities, and marginalization. I'll go quickly. So P of E, let's let that be the standalone probability for some proposition E and some collection of propositions, P of F, similarly for F. We can talk about the joint probability of E and F. We can talk about the conditional probability, where that vertical line should be read as given, probability of E given F. And then we have this neat factorization, which is at the heart of Bayes' theorem, that the joint probability E and F could be expressed as the conditional probability of E given F times the standalone probability of F. We can talk about marginalizing. If you take the joint probabilities of E and F and sum over F, you just get the standalone probability for E. And if I plug in the factorization here, I get this version of the marginalization formula. This will turn out to be very important. Actually, we'll see that the linearity of the relationship this establishes between P of F and P of E is ultimately responsible for the linearity of time evolution of quantum mechanics, which is otherwise mystery. All right, here's a conceptual invitation to this whole picture.
Do you have a conceptual, an interpretive framework of, should we think of this through Bayesian or frequentist? Or...
Oh, excellent question. So the answer, so the shallow answer is no. You're welcome to use whatever gloss of probability you want. The somewhat deeper answer is we are going to be writing probabilities into the laws. And so the most natural way to think about this is these are objective chance type probabilities. Now, whether you want to think of that in a frequentist sense, I mean, famously, it's very difficult to make probability, objective chance probability rigorous. I have some views on this. This is in the Q&A, maybe we'll talk about my views on this. But for now, we're going to be regarding these probabilities in a moment as part of the laws. And that makes sense because if you think about it, what's so special about determinism, right? Deterministic laws are actually a special case of probabilistic laws. And it would make more sense to start with a more general case and then justify the special case rather than trying to go the other way around. But we'll come back to this question of probability later. All right, so importantly, this talk will not be limited to any specific kind of quantum system, but I'm going to give you just a little entree into what's going to be going on and why it's important through the a single particle experiment, double slit experiment. So double slit experiment, you imagine sending particles one at a time. It's very important you send them one at a time. And people do this because they want to make it easy for you. They don't want to confuse you with two. They want to show you that it's like an effect that happens just one particle. They're not pulling the rug out from under you in any way by only doing one part at a time, right? I promise. Yeah. I'll explain why I'm being so cagey about that in a moment. All right, so you send particles one at a time toward a wall. It's got two slits in it, and you observe where the particle arrives on a screen, and you repeat many, many times. Okay, so this is the setup. The slits we assume are pretty close together. Let's let A denote starting conditions, variable starting conditions, B, which slit the particle goes through, and C, where it lands. All right, so the usual classical assumption, although this is usually not written down, but this is implicit in classical discussions, when they're trying to say, what do we expect classically will happen? This is what they're assuming. They're assuming that this formula holds. The conditional probability of where it lands, C, given the initial conditions A, can be expressed as the sum over which slit it goes through of the conditional probability of initial conditions, which slit it goes through conditioned on initial conditions, multiplied by the conditional probability of where it lands conditioned on what hole it goes through. This is just implicitly assumed. But of course, this doesn't follow from the general marginalization formula. This is not the marginalization formula I gave you before. This is a special assumption. It's a Markov assumption, right? That the moment it goes through a hole, we can just forget about the past and then restart the evolution at the holes. Right? This requires a Markov or divisibility assumption. And what you get is the following prediction. That curve there is the histogram of where the particle lands. It's actually a blend of two distributions because you condition the particle to the upper hole, you get like a normal-ish looking curve that's centered on the first hole. Similarly with the second hole, you blend them together, you get this distribution. And in fact, this does match observations from macroscopic particles like stones. Okay, for an electron or photon, famously, one gets what looks like an interference pattern over many trials. Does this mean the particle is really a Schrodinger wave, or that the particle somehow goes through both slits? Open up the intro chapter of volume 3 of Feynman's Lectures in Physics. That's what he says. He's very clear about that. But actually, we'll show that you can account for this pattern exactly as a formula. You can actually write down the correct formula merely by allowing the dynamics to be indivisible, remarkably. So basically, it'll be a breakdown of this formula. And what I'll do is I'll actually compute the discrepancy between these two formulas. And the answer will literally be the formula for interference. Okay, that's a good reason to maybe take seriously that we shouldn't be assuming the Markov approximation. All right, so to explain how this is all going to work, I need to go back and talk about dynamical systems. So there's a whole mathematical theory of dynamical systems. It's a rigorous mathematical subject. And it provides a simple mathematical model of a process with deterministic law. This is inspired by Hamiltonian mechanics. You pick a point phase space that has a position or configuration and a momentum. And then you have the famous Hamilton's equations of motion, first order equations. And in principle, if everything is good, you get a unique trajectory still cross. You get a really beautiful mathematical picture. So abstracting from this, a dynamical system consists of a state space or phase space. Each point in this space generally combines configuration and velocity, and a time-dependent dynamical map ft that just evolves each state. We'll label the states as I, an amount of time t. Right? So you give me a state I in the state space, you act with f of t, and it gives you a new state in the state space. And this is our deterministic law. F is our law. The standard definition of a dynamical system assumes that this law has a deterministic version of the Markov property. That just means you can evolve by t prime, then you can evolve by t. That's function composition there. And it's the same thing as just evolving by the combined t plus t prime. This is a standard assumption that one makes. Well, this mathematical construction is going to be too narrow. It's Markovian, it's deterministic. This is not what we want. Oh, on the other side, we have stochastic processes. So a stochastic process in the most general sense provides a simple mathematical model of a probabilistic process. And it consists of very minimal ingredients. There's a sample space, the set of things that can happen or can be observed, wherever you want to call it, and an initial probability distribution on that sample space, together with one or more time-dependent random variables. Okay? Random variables just assign values to different points in the sample space, and these can be time. All right, so given an element I of the sample space, we can assign an initial probability. These are the initial standalone probabilities P of I. They take values in the closed interval from 0 to 1. Given an element of the sample space and a time t, we can assign magnitudes to our random variables. I'll label these as a sub I of t. That's the ith magnitude or possible value of a random variable at time t, and they're real numbers. The expectation value of this random variable is that it's just a statistical average over p. So standard weighted average. We just sum on I of the magnitudes of this random variable over the standalone probabilities p sub I. Well, this mathematical construction is too broad. There's no law. There's nothing playing the role of f. There's nothing connecting moment to moment or establishing any kind of law for the evolution. Okay, well, in the paper, the first paper, the paper on the Stochastic-Quantum Theorem that I listed at the beginning, I generalized the notion of dynamical system to make it a little more hospitable to what we need. So I'll again take a state space together with a time-dependent dynamical map, but now I'm only going to assume this dynamical map evolves from some initial time 0 to another time t. I will not assume the Markov approximation. So we have deterministic law, but I'm not going to assume that if you give me some interval of time that doesn't start at 0, some time t prime to some other time t, I'm not going to assume that you can break things up and have evolution from 0 to t prime and then another well-defined map from t prime to t. So I will, in general, not assume that the evolution map will be divisible. Again, this is that notion of indivisibility introduced by Wolf and Schrock. They were working in the context of quantum channels, but the basic conceptual idea is the same. Now, of course, we could reimpose the Markov property and demand that if you evolve by t and then by t prime, you get the same thing as evolving by the sum of t plus t prime. That prime there should be on the t there in that second thing. It should be f of subscript t prime. But then we get back to standard definition of the dynamical system. So this is getting better, but it's still not probabilistic yet. So now we introduce the notion of a generalized stochastic system like I promised. Here we've got some configuration space C, that's playing the role of our sample space. We won't assume it's got momenta in there because that only really makes sense if you're doing deterministic evolution. We assume there's some initial probability distribution on the configuration space, just like in the case of a stochastic process. But now I will introduce a law. And that law is going to take the form of a time-dependent stochastic map, gamma sub t. So you give me J, an element of the configuration space. I have an initial standalone probability distribution just like before, Pj of 0. But I also have transition probabilities. Given the configuration system J at 0, rather than deterministically telling me the state or configuration of the system at later time t, now it's giving me a probability distribution over possible later configurations I at that later time t. Actually, I'm not even assuming that t is later than 0. T could be earlier, later. I'm not making any time irreversible assumptions here. And I'm going to call that collection of things gamma sub ij of t. Now, this is the Bayesian marginalization formula we saw before, right? Standalone probabilities at 0 multiplied by conditional probabilities summed on the initial configurations gives you the standalone probabilities at the later time t. This is just Bayesian marginalization. Notice it's a linear formula. And again, like I said, this is going to end up being responsible for the linearity of time evolution of quantum theory. This mathematical construction is now just right, like Goldilocks, just right.
So this
Yes.
configuration space that you're going to use, for example, in the in the say double slit experiment, would that be just three-dimensional space, or would it be different?
It would be three-dimensional space for
Okay.
one particle. Yep, very good. Yep, it's just what you think. These configuration spaces are going to be much more transparent than the usual spaces that we use in quantum theory. All right, so here's an intuitive description of a generalized stochastic process. The system, it's a physical system, is some configuration I from 1 to n in some set C called the configuration space. It could be infinite, but I'll assume it's discrete and finite just for the purposes of this talk. There's some discussion about the infinite case that you'll see later in the papers. This is just like classically. We would assign configurations just like we would do classically, just like you asked. And the system has laws that are stochastic. So the probabilities are built into the laws. The system has a conditional or transition probability to occupy its ith configuration at any time t, given that it occupies its jth configuration at each time 0.
Jacob,
Yes.
it kind of feels as if you're giving up the idea of using differential equations.
Yes.
You are,
I'm giving up the idea of differential equations.
okay,
Yes. Very good.
because you're saying that the probability just cares about when you start and when you end.
That's it.
Okay,
100% right. This is more general than a differential equation. And in fact, we'll see in what sense differential equations emerge from this picture. So it's an excellent point. Okay. And if it generalizes determinate dynamics equations motion, just like you said. Okay. Yes.
Could I ask something about the previous slide? You
Yes.
were saying
Which slide?
the one before. Well, you don't need to go there.
This one here?
You were saying right that there's no error of time. It's the time reversible invariant. I'm used to when there's probabilities, there is a difference, right? It's like first
Yeah.
something is fixed, and then there is no. What do probabilities still mean if there's no, they go in both directions?
There's nothing of a Bayes' law that says you can't condition on a later time and ask about an earlier time. That's it. It's just a more
Sure,
general fact. Now, of course, there can be systems that break time reversal invariance, but the formalism in general doesn't prescribe that that has to be the case.
Okay, I get that if it's just specifying our knowledge, I could see how.
Yeah.
But I thought you were saying it's objective.
Yeah,
Probability.
there's no reason. I mean, who says laws have to go only forward?
All right, that's cool.
Okay. So again, this approach is not connected with earlier stochastic formulations. Yeah.
I was just wondering, so would there be scope for a sort of initial value formulation of this sort of framework as well?
In the sense that you have initial data at 0 and then can make predictions at other times, yes, but not in the sense of the second order differential equation necessarily. Okay, so we'll introduce standalone probabilities at 0. They satisfy the usual rules, non-negativity, they sum to 1. We'll let P1 through Pn of t be the standalone probabilities at another time t. Again, they satisfy the same basic conditions. So again, they satisfy this is the same marginalization formula written before. Again, this is a linear relationship. You can arbitrarily change the initial probability distribution and then get the final probabilities. And again, we'll talk about the connection between this and the linearity of quantum, the evolution of quantum mechanics. All right, so the first step is to phrase this story in terms of matrices. The Bayes' marginalization formula very naturally adapts to matrix arithmetic. This is exactly the same formula written in terms of matrices. N by 1 column matrix of the final probabilities, N by 1 column matrix of initial probabilities, and an N by N matrix with all the conditional probabilities in it. So again, defining gamma ij to be those conditional probabilities, we get the following very nice matrix equation. It's actually a very nice way to introduce matrix multiplication. It's very naturally emerges here. So gamma of t consists of conditional probabilities, so it satisfies the two basic properties that define, mathematically speaking, a column stochastic matrix. It's a matrix, it's n by n, its entries are all non-negative, and its columns sum to 1. Okay, sum down each column is 1. Gamma of t is called the system's transition matrix. And for those of you who are familiar with Markov chains, this is a generalization of a Markov matrix. That's the properties that they satisfy. Although when people do Markov chains, sometimes they do row stochastic matrices, and it looks very ugly. I don't know why they do that. Okay.
These end up structurally more like finite difference sequences rather than differential equations.
In a way, although I'll complicate that a little bit. So hang on to that point. Yes, that's a good question. All right. So we're going to say general. Generality is the key here. The whole point is to start general and then appropriately derive special cases as we go. We're not going to assume that gamma of t describes a Markov process. So that we're not going to assume that we have a discrete time Markov chain that you can break time up into little bits delta t and then just multiply over and over again by some constant stochastic matrix gamma. We were not going to assume that. Less well-known approximation I keep coming back to is divisibility. Let me explain what this is in the case of our stochastic system. So divisibility in this sense is the idea that I can just act with my stochastic matrix to evolve from 0 to t prime. And then there's some other genuinely stochastic matrix, mathematical non-negative entries, that are good stochastic matrix that I can use to then subsequently evolve from t prime to t, and I get the same answer as if I just evolve from 0 to t. Our system will generically have indivisible stochastic dynamics. They will not generically exist that middle matrix there, gamma of t from t prime. That is a good stochastic matrix. And it's not hard to come up with examples. This is actually the generic case. This is a 2x2 example of an indivisible matrix. You can prove that this matrix does not divide. This is not a Markov chain matrix, and it's perfectly differentiable. It's a totally smooth matrix. It's just Gaussian in time. So it's well-defined for all t. It's differentiable. It's perfectly nice. But you can prove there is no such intermediate stochastic matrix that will bridge the gap, that will break the time of solution up. Here's another example. This one's periodic, obviously. So non-Markovian indivisible transition matrices like these are actually the norm of the general case. The first step in proving the Stochastic-Quantum Theorem is this statement. This is the dictionary. So here, theta is an n by n complex valued matrix. It is not unique, and actually leads to a whole other kind of gauge invariance that we're not going to talk about in this talk, but it's in the paper. It has some importance for symmetries. And here, pi and pj are n by n diagonal projectors. P sub I is just a matrix of zeros with a 1 in the ith diagonal entry. Super simple. So what do we have here? Well, we have a dictionary. It translates between generalized stochastic systems, whose law is contained in gamma ij of t on the left. And on the right, we have a trace over a Hilbert space and Hilbert space ingredients. This establishes this stochastic quantum correspondence that will let us translate between the two formulations with ease. Well, given that dictionary, if I take my initial standalone probabilities and just write them as the diagonal entries of an otherwise zero matrix, call that row of 0. It's an n by n matrix that's all zeros, but it has the standalone probabilities, the initial standalone probabilities of the diagonal. Then I can wrap it up in that theta matrix I introduced to define a time-dependent version that will generically not be diagonal anymore. I can take a random variable and all of its magnitudes and put them along the diagonal entries of an otherwise zero matrix. And then I have these really nice formulas. The ith standalone probability is given by the trace of the ith projector times rho. This is exactly the Born rule. And the expectation value of a random variable A is trace of the matrix A times rho of t. That's the standard formula for expectation values given a system with a density matrix rho. Oops, I've told you rho is a density matrix, but hang on. If the initial probability distribution happens to be classically pure, that is, if classically I know essentially with certainty exactly which configuration J my system starts out in, then you can show that that initial row of 0, well, it's just now going to only have a 1 in one entry, unit probability for exactly one configuration. That means it's going to be one of the projectors. So it's going to be one of the projectors. And then if we wrap it up with theta and theta dagger to define the time-dependent row over there, we're going to end up with a factorizable rank 1 matrix. It's expressible as psi of t times psi dagger of t for some n by 1 complex value vector, where that vector is theta of t acting on its initial value psi of t. This is beginning to look more and more familiar. In this case, those formulas at the top for the probabilities and expectation values, they simplify to the absolute value squared of the ith entry of psi. And the expectation value of A is obtained by taking A and wrapping it up in psi dagger psi. These are just the standard formulas that in fact, the formula there, psi I squared, was the original version of the Born rule that Born introduced in the 1920s. Notice, by the way, that psi here is really, if you just look at how it's defined, right? We start with definitely knowing the initial system's configuration, then we act with theta of t. All this is doing is pulling out one entry of the theta matrix. The theta matrix, by the dictionary, is encoding the dynamics of our system. So we see manifestly psi is just the jth column of theta. It's a derived law-like mathematical thing. It's not a physical object. It's made out of the laws. It's not a physical thing, the way that sometimes it's portrayed. Okay, well, these ingredients look familiar. Theta is playing the role of a time evolution operator, rho a density matrix, directly non-diagonal. Psi is playing the role of a state vector or wave function, and A is playing the role of a self-adjoint linear operator, although at this point still only diagonal. One can even go ahead and define a Heisenberg picture where you take the time evolution off of state vectors and density matrices and paste it onto the random variables. Here we have the original potentially explicit time dependence of the magnitudes on t, but now we've also pasted on implicit time dependence from theta, from the time evolution operator. Now, a composite system, so I've explained now what a generalized stochastic system is. I've explained the rudiments, the first step of how we prove this correspondence. But now I have to talk about what it means to have a subsystem in this formalism. So a composite system AB consisting of two subsystems A and B has a Cartesian product configuration space. This is true classically. It's also going to be true here for these generalized stochastic systems. Note, this is a Cartesian product.
Jacob,
Yes,
before we go here,
yes,
where is the Schrodinger equation?
it's coming up.
It is
In a
coming.
couple of
I need to
slides.
do this first.
Yes,
Okay.
yep, it's coming up in a couple of slides. We're trying to recreate all of quantum theory, so just, hey, we're getting there. So remember, configuration spaces are not, I haven't said, I've only briefly mentioned Hilbert spaces, but ultimately our stochastic system has some configuration space. If you've got two of them, then the configuration space is going to be, instead of all ordered pairs, it's going to be a Cartesian product, just like we would do classically. The dynamics, however, is going to be more complicated. If the two subsystems A and B are fully independent, just two completely, they don't know about each other, they don't talk to each other, independent stochastic systems, then the composite system's transition matrix will factorize as a tensor product, right? So this is where tensor products first enter into the story. These stochastic matrices are matrices, they've got two indices, and if I've got two systems that don't talk to each other, then I can think of the whole thing as one big system with two commuting independent stochastic matrices, and the way the indices work out is exactly a tensor product. So we can neatly identify, at this point, these were systems didn't know about each other. We can now identify in a very model-independent sense what an interaction is. An interaction is now going to be defined as the loss of this factorization. If this factorization breaks down, we go, oh, that was an interaction. We don't need to talk about forces or energy or anything like that, just directly in terms of these laws. We can phrase this breakdown and factorization the level of the composite system's time evolution operator. So the composite system has some theta, and when there's a breakdown in gamma, there's a breakdown in theta. It has to be a breakdown in theta. However, even if the time evolution operator theta refactorizes later times, this is crucial. Even if theta like briefly fails to factorize and then at a later time it refactorizes, the same won't be true for gamma. Theta and gamma are related by this sort of complicated dictionary. And so even if theta refactorizes, once gamma, the actual conditional probabilities, fail to factorize, they won't return to factorizing. Because of the indivisibility, they're encoding cumulative statistical information. And if they've ever interacted in the past, they're just going to fail to factorize at any point in the future. This sounds like entanglement, and we'll have more to say about this later. So time evolution operators give us a beautiful, general, precise way to define what it means for an interaction to occur. By the Stein-Spring dilation theorem from 1955, this is proved in the paper. I don't have time to show you the proof, but it's in the paper. If need be, by dilating that Hilbert space out of the correspondence appropriately, you can always assume that gamma is unistochastic. And this is this term unistochastic from 54, or I guess 1989. It was the modern version of the term. All the entries of gamma ij, all the entries of gamma, can be taken to be the squares, mod squares of the corresponding entries of a unitary matrix. This is not saying gamma is itself a unitary times a unitary. That would be matrix multiplication. This is more rudimentary. I'm saying each individual entry is the mod squared of the corresponding entry of some unitary. This is like a weird non-matrix arithmetic-like relationship. In the language of our dictionary, this statement becomes this. Gamma ij of t is trace of u dagger of t, pi, u of t, pj. This is just the dictionary way of writing the same statement. Here, U is unitary. A generalized stochastic system with this feature will be called a unistochastic system. If the stochastic matrix is expressible in terms of an underlying unitary in this way, we say it's a unistochastic system. And you might think unistochastic systems are therefore like a special case, but by the Stein-Spring dilation theorem, we can always regard our original system as being a subsystem of such a system, as I'll show in a moment, and that will ultimately establish the theorem. Well, if theta is now u, if the time evolution operator is now unitary, this is what happens to our formulas for the time development of state vectors and density matrices. These look very familiar formulas from textbook quantum theory. Generically, if we do this dilation, if we take our original system with its theta, time evolution operator, and we dilate the Hilbert space using Stein-Spring, we write that a potentially bigger Hilbert space in order to implement the dynamics in a unistochastic way. Well, in general, the time evolution operator for the bigger system, the dilated system, which will be unitary, the composite system's time evolution operator will fail to tensor factorize between the systems. The time evolution operator theta of t of our original system will fail to factor off of the other stuff we had to add. So what this means is our system, our original system, when we do this, may be interacting in some non-trivial way with the ancilla, with the stuff we had to add to do this dilation. And that means that our system may be forming correlations with the other stuff, that it is genuinely a subsystem of this bigger unistochastic system. But in any event, this proves the theorem. Every generalized stochastic system can be realized or regarded as a subsystem of a unistochastic system. System may be a bigger composite system that's evolving according to a unistochastic evolution law. And now we're golden. If U is a smooth function of T, and as long as we started with smooth functions of T for our, so we have our stochastic probabilities, they're saying at 0, we can then ask what's the conditional probability to be in some other configuration at time T. If that statement varies smoothly with T, then we'll have smooth dynamics. U of T can be taken to be a smooth function of T, and the rest is now going to be inevitable. We define a self-adjoint Hamiltonian from U in the standard way, by taking a derivative of U, multiplied by U dagger, and introducing I and H bar. This is where the complex numbers become very useful. And because the Hilbert space picture is make-believe, we can always add complex numbers for free. H bar here is just for units. Well, then you can just show you get the Schrodinger equation. Follows very easily here from the fact that psi of T is just U of T acting on psi of 0. We get the von Neumann equation for density matrices.
So Jacob,
Yes,
gamma is not Markovian, right?
correct, yes.
But now you're saying that this U fellow is.
Yes.
That's the key here.
That's the key. The
Okay.
fact that U has like a divisibility Markov property, which I'll show in just a moment,
Yeah, it is not at all
does
obvious.
not apply to gamma does. And I'll
Right,
come to that.
right,
I'll come to
yeah.
that point in a moment. Yep, that will actually be central to understanding this connection. All right, we have the Heisenberg equation of motion for Heisenberg picture observables. We have the Ehrenfest equation. Notice H of T, that Hamiltonian we've introduced, rho of T, Heisenberg picture observables. These will generically all be non-diagonal matrices. And these brackets are not Poisson brackets. This is not some tortured comparison or to Louisville class. These are actual commutators of matrices. These are the actual equations. The Schrodinger equation has emerged from a stochastic process, right? Which is just like amazing.
So what are they if they're not what's their expectation values?
Those brackets are commutators, A, B minus BA. That's literally how it shows up. Now, I'm going to come now to this question about discrete, like are we doing like difference equation type stuff? So here's unistochastic systems, which may seem a little exotic. They don't have to actually be so exotic. Consider a discrete dynamical system. So this is not a dynamical system. It evolves in a deterministic way, step by step by step over a time scale delta t. Okay. So in this case, the stochastic matrix will be a permutation matrix. That means that it's just zeros and ones, and we'll just shuffle around what configuration you're in as time goes by. So after n steps, gamma n delta t is just n copies of this permutation matrix. Well, every permutation matrix is unitary. And because the mod square of 0 and 1 is still 0 or 1, it's also unistochastic. So there you go. There's a unistochastic process. But actually, you could do more. So remember, the permutation matrix happens to be unitary, so its roots are well defined. You just diagonalize, take a root, and then undiagonalize. So you can define this permutation matrix to the power t over delta t and regard t as a smooth parameter. Everything is analytic. This is actually still going to be unitary. So if we square its entries, we will get a unistochastic dynamics. And this gives a beautiful analytic interpolation of our discrete deterministic process, where in the intervals between the discrete steps, we have probabilities that smoothly interpolate between steps. So actually the system will have a Hamiltonian, like a quantum Hamiltonian and a Schrodinger equation, even though it's a deterministic system. It's mind-blowing. Okay, so for n bigger than 2, you can show that an n by n unistochastic matrix will not generally be orthostochastic. That is, it will not generally be expressible as a real orthogonal matrix. That means that if you want to exploit the stochastic-quantum theorem and unitary evolution, you'll need the complex numbers or something algebraically equivalent to them. The complex numbers are also needed to be able to invoke the spectral theorem, symmetry generators, Hamiltonians, energy eigenvalues, stationary states, Schrodinger equation, all of that. So that's a good reason that when you design this Hilbert space picture, you're going to want to use the complex numbers. Actually, and this is an aside, if you want to do time reversal transformations, you have to introduce anti-unitary operators that are based on this complex conjugation operator K. K anti-commutes with I and squares to 1. It's involution. And that actually means if you take IK and IK, they generate a Clifford algebra called the pseudo-quaternions. And in some sense, Hilbert spaces are actually defined not just over the complex numbers, but over the pseudo-quaternions. That's just an interesting aside. All right, at this point, you might still wonder, well, okay, we had the Schrodinger equation, we have Hamiltonians, we have all this stuff, but we've only been talking so far about like diagonal observables, at least if you're looking at the Schrodinger picture. Bell might have called these beables, right? But don't all the observables of a genuine quantum system form a non-commutative algebra? What about all the non-commutative stuff? And what about supposedly signature or hallmark empirical features of quantum theory like interference and entanglement? Not to worry, the rest will naturally emerge. In particular, non-diagonal observables we'll see will be emergent patterns in the dynamics. So it's beables, they'll be called emergibles. The set of observables for a quantum system will consist of its beables. These are the things that are random variables, well-defined, familiar-looking random variables on the underlying stochastic system's configuration space, and they'll correspond to diagonal matrices. But there'll also be all these other non-diagonal self-adjoint operators, and those will also be measurable in experiments. So beables are the things present in the configuration space. The emergibles will be emergent features of dynamics. Now I'm going to address Ramesh's question. So we can always assume our system is or is embedded in a unit stochastic system. That means there's a unitary time evolution operator. We can use unitarity to define a relative time evolution operator. You just take u of t multiplied by u dagger of any other time t prime. This defines a relative time evolution operator that takes you from t prime to t. And then we get the following composition law or semigroup property. I don't want to call it Markovian because these aren't probabilities anymore, but it does look like a Markov property. And you might wonder, well, if the time evolution operator satisfies this property, I can evolve from 0 to t prime and then separately from t prime to t, and then I get the same thing as if I evolve from 0 to t prime to t, and then 0 to t. Why can't I do the same thing for gamma? It's because gamma, those stochastic probabilities, are not related in a simple way to u. However, you can show that if you take that U matrix in the middle that we just introduced and square its entries, you do get a properly unistochastic matrix. And you might wonder, does this satisfy a corresponding divisibility or Markov law? The answer is not. You can show that gamma of t is not equal to taking that gamma we introduced and multiplying it by gamma of t prime. They're not equal. And in fact, if you compute the difference between them, you get that formula, which is literally the formula for interference. This is exactly the formula for quantum mechanical interference. You get a bunch of cross terms. This is the formula for interference. And so what we see is that what we think of as interference isn't really about cats being both alive and dead or particles going through both holes. It's just if you have a system that's not Markovian, and you either empirically measure the results or theoretically predict the results, and then you compare that to the closest Markovian approximation, you'll get a discrepancy, and that discrepancy is exactly interference. So in principle, you could find interference in any non-Markovian system, stock market, anything that's not exactly Markovian. We didn't need to invoke Schrodinger waves here. Unfortunate accident of history that so many early examples of quantum mechanical interference resembled wave interference in 3D. Wave functions don't even usually live in 3D space. And this is why, they're like, oh, we're just going to give you one particle at a time to keep things simple. They're actually being a little deceptive. If you have two particles, the wave function would literally live in 6-dimensional space. And then you certainly wouldn't be talking about waves going through holes because those walls don't live in 6-dimensional space. Schrodinger knew this. He pointed this out originally in his first paper, early papers in 1926, introducing what he called undulatory mechanics or wave mechanics. Einstein openly disliked the idea that configuration space was the seat of reality, although Schrodinger tried to push that. And particles live in a configuration space of dimension 3n. And of course, there are abstract systems like qubits that don't even have a continuous configuration space at all. Now we finally have a framework that lets us explain on theoretical grounds why the Markov approximation works so well. Consider a composite system. We now have a language of composite systems, a subject system and an environment that we'll assume is unistochastic. Suppose that for each configuration I of the subject system, the environment has a corresponding configuration E of I, a configuration that corresponds to the environment has seen the configuration I. And suppose that whatever dynamics happens, it leads to, at time t prime, a classical correlation between the configurations of the subject system and the environment. The subject system has some probability distribution to have its various configuration values at time t prime, and then whatever that configuration is, the environment definitely has the corresponding configuration. Assume at least for a little time, there are no interactions between the two systems, so they have their own dynamics, and we can define dynamics for them. Well, then just by classical marginalization, there's no partial traces or Hilbert spaces here, just classical marginalization, what you can show is that we get an emergent Markov law for the subject system alone after we marginalize over the environment. This is just calculation you can do. So now there is a well-defined gamma S of t that really does carry out evolution from t prime to t. That is, due to the correlating interaction in the environment at T prime, there is a new division event, T prime, that plays the new role of T equals 0. So 0 is not actually a special time. If you've got an environment checking in, eavesdropping on your system, you'll get more T equals 0s times when you can restart the evolution. These are the division events.
Those are the measurements.
Exactly what measurements are. Division events are then going to be ubiquitous for open systems and noisy eavesdropping environments, and that's why the Markov approximation works so well. This is the first principles explanation of the Markov approximation. Notice this will also kill interference, because now the difference between gamma S and this sort of factorization is 0. That's why interference disappears. That's why it disappears in the double slit experiment if you observe which hole the particle goes through. So it's easy to show that at time T prime, if you compute the reduced density matrix of the subject system, it'll momentarily become diagonal. And this is exactly what decoherence is. All those off-diagonal entries, the coherences will go away. So we learned that those off-diagonal entries in the density matrix, those correspond to superpositions and state vectors, are just a mathematical artifact. They're just recording the failure of divisibility or Markovianity. And decoherence is just on the Hilbert space side what on the stochastic side is just the mundane leakage of correlations in the environment looks like. Let me talk about entanglement. So even in classical deterministic systems, during an interaction, systems will have non-factorizing dynamics. While systems are interacting, you won't be able to write separate dynamics for two systems. Given two systems A and B, again, if they're not yet interacting, they're not interacting from 0 up to just before some later time T prime, then again, they will have factorizing dynamics. However, because transition matrices, again, encode cumulative statistical information, if they interact at T prime, then at least until we get to the division event, we're going to have failure of factorization. They will not have factorizing dynamics. This looks like entanglement. But if then later, after the systems are separated and are no longer interacting, there's a division event. Maybe the environment checks in on what one of the systems is doing. Then there'll be a breakage of the indivisibility. There'll be a new division event. There'll be a well-defined new stochastic matrix going from T double prime, the eavesdropping moment, to later times T. And if the systems have not been interacting at that point and are still interacting, that will go back to factorizing, and that's the breaking of entanglement. All seen through the lens of the stochastic process. Okay, the measurement story I'm going to have to skip because we're out of time. But let me just say that once you can talk about interference and measure interference, once you can talk about entanglement, it's very easy now to just run through a measuring process. Replace the environment with a measuring device together with an environment. The measuring device will also have configurations that correspond to reading the system. And what you'll find is if you just run this story for an arbitrary non-diagonal self-adjoint operator, what you find is the system will end up, just some details of like how you implement this, but it's not hard. It's a textbook, unitary evolution from a textbook. What you find is that the probability for the measuring device to end up in its configuration d alpha prime, this is the configuration in which it's read one of the values of the subject system, is given by the absolute value squared of the subject system's wave function in that basis. Like this just falls out of the stochastic dynamics. It's a calculation you can do. So stochastically, there's just some overall stochastic process that has a measuring device and environment of subject system in it. And if you just let it evolve, the measuring device will just probabilistically end up in one of its measurement configurations with a probability that you can calculate is exactly given by the Born rule. This is the textbook Born rule for the probability of an appropriate measurement outcome. And you can show, because these are all just stochastic probabilities, I can actually condition on that measurement results and then predict what the subject system is going to do. And I find that what happens is I get a similar looking probability formula for how you compute standalone probabilities, but now with a modified density matrix that is conditioning on the measurement result by the device. I assign the subject system a new density matrix that gives me the correct conditional probabilities. And it's exactly the wave function collapse density matrix. Okay. So this is textbook wave function collapse. All right, this is the end. This is the concluding slide. So this approach explains where linearity and unitarity in Hilbert spaces come from. They're no longer posits. It explains why we use the complex numbers. We're free to use them. They give us all these cool things, and if you throw them out, you'd still have the same stochastic process. It'd just be harder to use. It deflates some folklore. For example, in this picture, superposition is no longer taken literally. Measuring devices are now ordinary systems, and we have a definition of a measuring device, which you don't have in standard quantum mechanics. They're just a system that has enough configurations to do the readings, the right overall stochastic dynamics, which is the responsibility of the good experimentalist to put together, and in an environment to ensure good, robust division events. So arguably, from this standpoint, no longer a measuring problem. We get a clear interpretation of the insert principle, which I couldn't talk about today, navigates all the no-go theorems you can check. It's no more non-local than textbook quantum theory. In particular, new correlations only form locally, and meshes very nicely with special relativity, where you replace division events with hypersurfaces in spacetime. Gives new ways to think about and maybe even generalized dynamical symmetries, which I couldn't talk about today. There are some implications for old problems in statistical mechanics because we're no longer trying to get stochastic rules and laws out of an underlying deterministic microphysics. Now that we have stochasticity in the microphysics, a lot of old questions in statistical mechanics just dissolve. It'd be interesting to explore ramifications of this approach for algebra first approaches, like famously the problem of unitarily inequivalent representations. This is the connection to quantum computing. Maybe there are new algorithms for simulating non-Markovian indivisible real-world systems on quantum computers with many applications. It would be useful to construct some explicit models of this correspondence for particular kinds of quantum systems that show up in Gauss matter, quantum field theory, and so forth. This gives you a platform for potentially generalizing quantum theory itself. And most importantly for today, there are potential implications for quantum gravity. We don't have a probabilistic generalization of general relativity. The claim is that maybe if we did, that would just be quantum gravity. Because if ultimately quantum mechanics can be boiled down to just a very general stochastic process, maybe a general stochastic version of general relativity would just be the answer. And it is very interesting that we don't have one today, but maybe we should get to working on that. That's it. Thank you.
Okay, thank you, Jacob. Maybe we can just take a few questions and I'll keep an eye on the chat, especially if there are questions from
Looks like there's one, right?
Zoom participants.
I think it's surplus.
Clapping. Okay, so
Please go ahead.
Maybe on the last note, like it also gets back to motivation you mentioned earlier, like, oh, the deterministic case is a stressful case of the general stochastic one. So why not focus on the general case? But like GR, if you have a deterministic theory, forgetting about singularities, why would you want to add indeterminism, which I assume is implied by making it stochastic? Like, I see if it's the best we can do to get a stochastic theory, sure, but if we already have GR, why would it seems like creating problems to wanting to have a stochastic?
This is a great question. If all we knew about was general relativity and we didn't know about quantum mechanics, then I guess it'd be great. And certainly Einstein was pretty happy having a deterministic theory and so forth. The claim is that the proper way to understand quantum mechanics is that it's really just a mathematical gloss over a stochastic process. So unless we're going to throw quantum mechanics out the door or replace it with the deterministic theory, it does look like we need GR to be probabilistic in some sense. But maybe not. Maybe there is some secretly deterministic story under quantum mechanics. We don't know. But it is still interesting that we don't have a general probabilistic version of GR. It's a very interesting one. And historically, it kind of makes sense, right? I mean, GR was done in 1915, 1916. And you don't even have Markov processes becoming widely used until the 50s, right? Like, so like, it was just, and by then people, I mean, so, and of course, quantum gravity, people were working on quantum gravity already by the 1920s and 30s, right? So like, I just think historically stuff happened out of order. It'd be interesting to know what would have happened if history happened in a different order. Ramesh.
So, right in the middle of your talk, there's one piece of magic, mathematical magic, which just kind of went fast.
Yes.
And I didn't get it.
Yes.
So, there is the probability matrix, the gammas. And you said, look, that guy is not, you can't just do it in pieces. It's beginning and non-Markovian.
Yes.
Okay. And then it just satisfies certain rules, columns should add up to 1 and all that stuff.
Yes.
Then you said this guy can always be written as some mod u squared for each element. Well, I can believe that because these are positive numbers. I can write it as mod u squared.
Yes.
But then you said that u fellow
Is unitary.
is unitary.
Correct.
That I did not get.
That's not obvious, and that's the core of the theorem. I can sketch out to you how the theorem works.
And this is what the Steinbring 1954 or
That's
whatever.
right. That's the Steinbring dilation theorem. So I can just sketch it out.
Yeah.
The first step is actually to do what you just said, write the entries as the mod squares of another matrix that's not unitary. Then the magic, and this is totally surprising, is that the time evolution number you get when you do this, it's not unitary, but it turns out to be provably a quantum channel, a completely positive trace preserving map. And then the Steinbring theorem applies. If the Steinbring theorem says if you have a Hilbert space evolving by a completely positive map, there is, if need be, a bigger Hilbert space of bounded dimension. It's not arbitrarily higher dimension. You have to add at most a couple of degrees of freedom, or even 1 with enough values in it. And then in that bigger Hilbert space, there will be unitary evolution. So the magic is really coming out of the Stein-Spring dilation theorem. And there's like a sketch of a proof of it in the paper. So you can actually, and all this is totally non-obvious, and it's not how these theorems were historically used or how they're currently used. They're being used in a very different way. So it is, this is magic.
Fine. It
I
looks like
mean,
magic to me.
It is.
I thought you were going to team magic by it.
It's magic.
Magic, yeah, right.
Yeah.
Okay, thank you.
So, like, just on that, so you're adding more degrees of freedom to be able to diagonalize the evolution operator roughly.
To be able to write it as a unitary
Unitary,
evolution operator. That doesn't mean to say
That's
I.
one, right,
Yeah.
that's right. So, but still, we're talking about the indices of gamma ij are configuration space,
Correct.
and you've added multiple degrees of freedom there. So
You
what
also
do
added
these-
into there, that's right.
Right, so what do these correspond to? Like, what are the physical degrees of freedom?
That's a wonderful question, and one I didn't have time to talk about, but I'll say briefly here. So once you dilate on the Hilbert space side, you have like a bigger quantum system, and then you can read the correspondence backward, and you'll have some bigger generalized stochastic system with unistochastic dynamics that your original system will be a subsystem of. At one level, you could just say these are formal. I just added these for convenience. But interestingly, there's a very special case in which adding these things is very important. Suppose I give you a quantum system like a particle, let's say, and suppose it's got spin. Suppose it's a spin half particle, right? You know that its Hilbert space is the usual infinite dimensional Hilbert space of the particle, position degrees of freedom, tensor producted with this finite dimensional spin Hilbert space. And it's evolving, it's got unitary dynamics, whatever. Remove the spin. Go down to the smaller Hilbert space where we throw spin out, right? You can regard the particle without spin as being like a subsystem of the full Hilbert space. What you'll find is the dynamics is no longer unitary. Okay. The Stein-Spring dilation is just the opposite operation. You start with some system that looks non-unitary, you add something, now it's unitary, and that something may not have any physical meaning at the level of the underlying configuration space. It could be like a spin degree of freedom that doesn't have a nice classical interpretation. But by adding it, you now have unitary evolution. And those spin variables, the spin operators, even though they may not have a clear meaning at the level of the stochastic process, they're emergibles. You can still have a measuring device interact with them and yield results on them through this measuring process. When a measuring device measures something that it's an emergible, it's not telling you what the system, like what configuration it's secretly in, but it is recording some emergent feature of the dynamics that will lead to results on a measuring apparatus with the Born rule probabilities. So for all observable purposes, spin will look just like any ordinary observable as far as all external apparatuses are concerned. In a sense, this realizes Niels Bohr's original argument against the EPR paper. Niels Bohr said, when you measure something, really the measurement outcome is this emergent interplay between measuring device and system. It's not really telling you what the system is doing. This is a slightly more nuanced version of that. There are features of the system, the random variables, the beables. When you measure those, you really are finding out what the system is doing. But some of the observables are these emergibles, these non-commutative things, and they lead to measurement results in this sort of emergent way. From the point of view of an external measuring device, they can't tell the difference. And if you got rid of the beables, you would have emergence from nothing. There'd be no physical substrate at all. The beables, the configuration spaces, they give you a physical substrate, a thing from which everything else is supposed to emerge. That's the ingredient that's being added here. So it's not that we're saying Bohr is wrong, and it's not that we're saying, really, the answer is some kind of like compromise between all these different positions. Some observables are really reflecting what the system is doing, those are the beables, and that gives you something from which everything else can emerge, and other observables are these sort of emergent patterns that show up. For example, after you do a dilation. So in some cases, the dilation does give you things that are measurable. And of course, they were there all along, right? I mean, dilating didn't actually change the stochastic system. It's just that they made manifest certain emergent features that measuring devices can go out and measure.
I have a few more questions, but I guess we have to.
We need to.
We should wrap
Yeah.
it up. Okay, everybody, thank you. Thank you.
I'm happy to take more
Boy.
questions. We can chat.
Thanks, everyone.